Welcome back, guys. Our subject is Math3E Differential Equations, and this is Lecture 2. So we are still under Chapter 1, Introduction or Definition. Our lesson for today is Solution of a Differential Equation. Under this topic, we have analytic theorems of determining the solution of a DE and graphical method of finding the solution of a DE. Analytic theorems of determining the solution of a DE. An nth-order ordinary differential equation is an equality relating the independent variable to the nth derivative of the dependent variable. Examples are, our first example is a second order with x independent and y dependent. Our second example is a second order t independent and y dependent. And our third example is a fourth order t independent and x dependent. Thus, a general form of an nth order equation with x independent, y dependent can be expressed as f of x, y, dy over dx up to the nth derivative of y with respect to x equal to 0, where f is a function that depends on x, y, and the derivatives of y up to order n, that is on x, y, up to dy over dx. We assume that the equation holds for all x in an open interval I. In many cases, we can isolate the highest order term, this of ny over dx of n, and write the equation as this of ny over dx of n is equal to the function of x, y, dy over dx up to this of n minus 1 y over dx of n minus 1, which is often preferable to equation 1 for theoretical and computational purposes. Explicit solution. A function phi of x that when substituted for y in equation 1 satisfies the equation for all x in the interval I is called an explicit solution to the equation on I. Example 1. Show that phi of x equal to x squared minus x raised to negative 1 is an explicit solution to the linear equation d squared y over dx squared minus 2y over x squared equal to 0, but psi of x equal to x cubed is not. Okay, so here is our solution. First, we write phi of x equal to x squared minus x raised to negative 1. And then we get the first derivative, which is equal to 2x plus x raised to negative 2. And the second derivative, which is equal to 2 minus 2x raised to negative 3. And then we write our differential equation. And then we substitute the values of the derivatives. Okay, this is equal to x squared minus x raised to negative 1 equal to 0. And we simplify, which is equal to 2 minus 2x raised to negative 3 minus this cancels out. So, magiging siyang 2 plus 2 plus 2x raised to negative 3 equal to 0. Okay, so as we can see, all the terms cancel out, which is equal to 0 equal to 0. So it means it is a solution. Now let's try psi of x equal to x cubed. We get the first derivative, which is equal to 3x squared. And the second derivative is equal to 6x. Then we write again the differential equation. and we substitute the values of the derivatives. That is equal to 6x minus 2x cubed over x squared equal to 0. Simplifying, we get 6x minus 2x equal to 0. Then 4x equal to 0, which is valid only when x is equal to 0. Since this is valid for any x not equal to 0, the function phi of x equal to x squared minus x raised to negative 1 is an explicit solution to our differential equation on the interval negative infinity to 0 and also on 0 to positive infinity. For psi of x equal to x cubed, we have 4x equal to 0, which is valid only at the point x equal to 0 and not on an interval. Hence, psi of x is not a solution. Example 2 showed that for any choice of the constants c1 and c2, the function phi of x equal to c1e raised to negative x plus c2e raised to 2x is an explicit solution to the linear equation y double prime minus y prime minus 2y equal to 0. Okay, so here is our solution for example 2. We compute p prime of x equal to negative c1 e raised to negative x plus 2 c2 e raised to 2x. Then we get the second derivative, which is equal to c1e raised to negative x plus 4c2e raised to 2x. Then we write our differential equation y double prime minus y prime minus 2y equal to 0. And substitution of phi prime and phi double prime for y prime and y double prime in the equation yields. So now we are simplifying our equation. This term is positive c1e is negative x minus 2 c2e is to 2x minus 2 c1e is to negative x minus 2c2e raised to 2x. Further simplification, so we combine like terms. Okay, so as we can see, all the terms cancel out. Therefore, 0 equal to 0. Okay, so since equality holds for all x in the interval negative infinity to positive infinity, then phi of x equal to c1e raised to negative x plus c2e raised to 2x is an explicit solution to the differential equation on the interval negative infinity to positive infinity for any choice of the constants c1 and c2. As we will see in chapter 2, the methods for solving differential equations do not always yield an explicit solution for the equation. We may have to settle for a solution that is defined implicitly. So we consider the following example. Example 3 showed that the relation y squared minus x cubed plus 8 equal to 0 implicitly defines a solution to the nonlinear equation dy over dx equal to 3x squared all over 2y on the interval 2 to positive infinity. Okay, so here is the solution for example 3. We first solve for y. So we get y squared equal to x cubed minus 8. So y is equals to positive or negative square root of x cubed minus 8. And then we get the first derivative of y is equals to square root of x cubed minus 8. So we solve for the first derivative. So our first derivative is 3x squared all over 2 square root of x cubed minus 8. And then we write our differential equation dy over dx is equal to 3x squared all over 2y. And then we substitute the values. So we can see that it is equal to 3x squared over 2 square root of x cubed minus 8 is equal to 3x squared all over 2 square root of x cubed minus 8. So we see an identity. Okay, so it is indeed an explicit solution to a differential equation. Also, you can check the value of psi of x equal to negative square root of x cubed minus 8 is also an explicit solution. Kasi yung pinakita nating solution is we only use the principal root, which is the positive root. Implicit solution. A relation g of x and y equal to 0 is said to be an implicit solution to equation 1 on the interval I if it defines one or more explicit solutions on I. Example 4. Show that x plus y plus e raised to xy equal to 0 is an implicit solution to the nonlinear equation quantity 1 plus x e raised to xy dy over dx plus 1 plus y e raised to xy is equal to 0. So here is the solution. First, we observe that we are unable to solve equation 7 directly for y in terms of x alone. However, for equation 7 to hold, we realize that any change in x requires a change in y. So we expect the relation 7 to define implicitly at least one function y of x. This is difficult to show directly, but can be rigorously verified using the implicit function theorem of advanced calculus, which guarantees that such a function exists that is also differentiable. Once we know that y is a differentiable function of x, we can use the technique of implicit differentiation. Indeed, from equation 7, we obtain on differentiating with respect to x and applying the product and chain rules. Okay, so we get the first derivative of the function with respect to x. So we perform implicit differentiation. So we obtain the value 1 plus dy over dx plus e raised to xy times y plus x dy over dx equal to 0. Or simplifying, we obtain quantity 1 plus x e raised to xy dy over dx plus 1 plus y e raised to xy equal to 0, which is identical to the differential equation. Thus, the relation 7 is an implicit solution on some interval guaranteed by the implicit function theorem. For example 5, verify that for every constant c, the relation 4x squared minus y squared equal to c is an implicit solution to y dy over dx minus 4x equal to 0. Graph the solution curves for c equal to 0, positive or negative 1, positive or negative 4. Okay, so the solution, when we implicitly differentiate the equation 4x squared minus y squared equal to c with respect to x, we find 8x minus 2y dy over dx equal to 0, which is equivalent to equation 9. In figure 1.4, we have sketched the implicit solutions for c. Okay, so here is our figure 1.4. The curves are hyperbolas with common asymptotes. Y is equals to positive or negative 2x. Notice that the implicit solution curves fill the entire plane and are non-intersecting for c not equal to 0. For c equal to 0, the implicit solution gives rise to the two explicit solutions. Y is equals to 2x and y is equals to negative 2x, both of which pass through the origin. Initial value problem. By an initial value problem for an nth-order differential equation, we mean find a solution to the differential equation on an interval I that satisfies at x of 0 the n initial conditions. That is, y of x of 0 is equals to y of 0, dy over dx of x of 0 is equals to y1, up to the this of n minus 1 y over dx of n minus 1 of x of 0 is equals to y of n minus 1, where x of 0 is an element of I, and y of 0, y of 1, up to y of n minus 1 are given constants. In the case of the first order equation, the initial conditions reduce to the single requirement. That is, y of x of 0 is equal to y of 0. And in case of a second order equation, the initial conditions have the form x of 0 is equals to y of 0 and dy over dx of x of 0 is equals to y1. The terminology initial conditions comes from mechanics, where the independent variable x represents time and is customarily symbolized as t. Then if t sub 0 is the starting time, y sub t sub 0 is equals to y sub 0 represents the initial location of an object, y prime sub t sub 0, and gives its initial velocity. Example 6. Show that phi of x equal to sine x minus cos x is a solution to the initial value problem d squared y over dx squared plus y equal to 0. Initial conditions, y sub 0 is equal to negative 1 and dy over dx of 0 is equal to 1. Okay, so here is the solution for example 6. We get the first derivative with respect to x, that is equal to cosine of x plus sine of x. Then we get the second derivative with respect to x, that is negative sine of x plus cosine of x. Then we substitute the initial values or initial conditions. At y sub 0 equal to negative 1. So at x equal to 0, y is negative 1. So sine 0 minus cosine of 0 is equal to negative 1. Sine 0 is 0, cosine of 0 is 1. So minus 1 equal to negative 1. Thus negative 1 equal to negative 1. Okay, so we get the second initial condition, that is dy over dx of 0 equal to 1. So at x is 0, dy over dx equal to 1. So cosine of 0 plus sine 0 equal to 1. So that is 1 plus 0 equal to 1. So 1 is equals to 1. Okay, so as we can see, hence, phi of x is a solution to the differential equation. When we check the initial conditions, we find that it is an identity, which meets the requirements of the equation 10. Therefore, phi of x is a solution to the given initial value problem. Example 7, as shown in example 2, the function phi of x equal to c1e raised to negative x plus c2e raised to 2x is a solution to d squared y over dx squared minus dy over dx minus 2y equal to 0 for any choice of the constants c1 and c2. Determine c1 and c2 so that the initial conditions y of 0 equal to 2 and dy over dx of 0 is equal to negative 3 are satisfied. Okay, so this is our solution to example 7. So we first substitute the initial condition. That is y of 0 equal to 2. Kasi na-prove na natin na yung phi of x is a solution to our differential equation dun sa example 2. So, yung equation 1 natin, c1 plus c2 is equals to 2. Okay, so we now solve for the second condition. That is dy over dx of 0 equals to negative 3. So again, nasolve na din natin dun yung first derivative natin and substituting the values, that is at x is 0, dy over dx must be equal to negative 3. Okay, so we obtain negative c1 plus 2c2 equal to negative 3. That is our equation 2. So we sum up the two equations. Okay, so summing up, makakancel yung c1, ang matitira is 3c2 is equals to negative 1. Therefore, c2 is equals to negative 1/3. Then substituting the value for c2, so ma-obtain natin na c1 is equals to 7 over 3. So ito na yung values natin ng c1 and c2. Okay, so substituting for c1 and c2, we obtain a particular solution. Phi of x is equals to 7 over 3 e raised to negative x minus 1/3 e raised to 2x. Yan. Okay, hence the solution to the initial value problem is phi of x equal to 7 over 3 e raised to negative x minus 1/3 e raised to 2x. We now state an existence and uniqueness theorem for first-order initial value problems. We presume that differential equation has been cast into the format dy over dx is equals to the function of x and y. Of course, the right-hand side, f of x and y, must be well defined at the starting value x of 0 for x and at the stipulated initial value y of 0, that is, y of x of 0 for y. The hypotheses of the theorem, moreover, require continuity on both f and partial derivative of f with respect to y for x in some interval a to b, containing x of 0, and for y in some interval c to d, containing y of 0. Notice that the set of points in the xy plane that satisfy the value of x on the interval a to b and the value of y in the interval c to d constitutes a rectangle. Figure 1.5 depicts this rectangle of continuity with the initial point in its interior and a sketch of a portion of the solution curve contained therein. Existence and uniqueness of solution. Theorem 1. Consider the initial value problem. Dy over dx is equal to the function of x and y, and y of x of 0 is equal to y of 0. If f and the partial derivative of f with respect to y are continuous functions in some rectangle that contains the point x of 0, y of 0, then the initial value problem has a unique solution, phi of x in some interval x of 0 minus delta up to x of 0 plus delta, where delta is a positive number. Okay, so here is figure 1.5, layout of the existence uniqueness theorem. So we can see that there is a rectangular domain wherein the point x of 0, y of 0 is inside this rectangular domain, and the edges of this rectangle is the interval a to b on the x-axis and c to d on the y-axis. The preceding theorem tells us two things. First, when an equation satisfies the hypothesis of theorem 1, we are assured that a solution to the initial value problem exists. Naturally, it is desirable to know whether the equation we are trying to solve actually has a solution before we spend too much time trying to solve it. Second, when the hypotheses are satisfied, there is a unique solution to the initial value problem. This uniqueness tells us that if we can find a solution, then it is the only solution for the initial value problem. Graphically, the theorem says that there is only one solution curve that passes through the point x of 0, y of 0. In other words, for this first order equation, two solutions cannot cross anywhere in the rectangle. Notice that the existence and uniqueness of the solution holds only in some neighborhood x of 0 minus delta to x of 0 plus delta. Unfortunately, the theorem does not tell us the span or 2 delta of this neighborhood that is merely not 0. When initial value problems are used to model physical phenomena, many practitioners tacitly presume the conclusions of Theorem 1 to be valid. Indeed, for the initial value problem to be reasonable model, we certainly expect to have a solution since physically something does happen. Moreover, the solution should be unique in those cases where repetition of the experiment under identical conditions yields the same results. Okay, example 8. For the initial value problem, 3 dy over dx equal to x squared minus xy cubed and y sub 1 equal to 6. Does theorem 1 imply the existence of a unique solution? Okay, so here is the solution for example 8. We first divide both sides by 3, so we get dy over dx is equal to x squared minus x y cubed all over 3. This is fx. And we get the partial derivative of f with respect to y. So that is yung first term, 0. So matitira negative x. Then derivative of y cubed is 3y squared all over 3 is equal to negative xy squared. Dividing by 3 to conform to the statement of the theorem, we identify yung f of x and y, yung nasolve natin kanina, and yung partial derivative niya with respect to y. Both of these functions are continuous in any rectangle containing point 1, 6. So the hypotheses of theorem 1 are satisfied. It then follows from the theorem that the initial value problem has a unique solution in an interval about x equal to 1 of the form 1 minus delta, 1 plus delta, where delta is some positive number. Okay, we have example 9. For the initial value problem, dy over dx is equal to 3y raised to 2 thirds and y sub 2 equal to 0. Does theorem 1 imply the existence of a unique solution? Okay, so here is our solution to example 9. We have f of x and y is equals to 3y raised to 2 thirds. So we get the partial derivative of f with respect to y. So by power rule, we have 2 thirds times yung coefficient 3. So y raised to negative 1 third. Simplifying, we obtain 2y raised to negative 1 third or 2 all over cube root of y. Okay, so when y is 0, we see that the partial derivative of f with respect to y is undefined. Okay, so unfortunately, the partial derivative of f with respect to y is not continuous or even defined when y is 0. Kasi nga, yung nakuha nating value na 2 all over the cube root of y, when y is 0, magiging siyang undefined. Kasi a number divided by 0. Consequently, there is no rectangle containing 2, 0 in which both f and partial derivative of f with respect to y are continuous. Because the hypotheses of Theorem 1 do not hold, we cannot use Theorem 1 to determine whether the initial value problem does or does not have a unique solution. It turns out that this initial value problem has more than one solution. In example 9, suppose the initial condition is changed to y sub 2 equal to 1. Then, since f and partial derivative of f with respect to y are continuous in any rectangle that contains the point 2, 1 but does not intersect the x-axis, it follows from Theorem 1 that this new initial value problem has a unique solution in some interval about x equal to 2. Graphical method of finding the solution of a DE. So we have direction fields. The existence and uniqueness theorem discussed in the previous lessons certainly has a great value, but it stops short of telling us anything about the nature of the solution to a differential equation. In practical reasons, we may need to know the value of solution at a certain point, or the intervals where the solution is increasing, or the points where the solution attains a maximum value. Certainly, knowing an explicit representation for the solution would be a considerable help in answering these questions. However, many of the differential equations that we are likely to encounter in real-world applications, it will be impossible to find such a formula. Moreover, even if we are lucky enough to obtain an implicit solution, using this relationship to determine an explicit form may be difficult. Thus, we must rely on other methods to analyze or approximate the solution. One technique that is useful in visualizing the solutions to a first-order differential equation is to sketch the direction field for the equation. To describe this method, we need to make a general observation. Namely, a first-order equation, dy over dx, a function of x and y, specifies a slope at each point in the xy plane where f is defined. In other words, it gives a direction that a graph of a solution to the equation must have at each point. Consider, for example, the equation dy over dx is equal to x squared minus y. The graph of a solution to equation 1 that passes through the point -2, 1 must have a slope 3 at that point, and the solution through -1, 1 has 0 slope at that point. A plot of short line segments drawn at various points in the xy plane showing the slope of the solution curve there is called a direction field for the differential equation. Because the direction field gives the flow of solutions, it facilitates the drawing of any particular solution, such as the solution to an initial value problem. In figure 1.6a, we have sketched the direction field for equation 1, and in figure 1.6b, have drawn several solution curves in color. So here is yung figure 1.6. Some other interesting direction field patterns are displayed in figure 1.7. Depicted in figure 1.7a is the pattern for the radioactive decay equation dy over dx is equal to 2y. So yung radioactive decay equation, usually may encounter natin siya sa chapter 3 sa applications. From the flow patterns, we can see that all solutions tend asymptotically to the positive x-axis as x gets larger. In other words, any material decaying according to this law eventually dwindles to practically nothing. This is consistent with the solution formula A is equals to CE raised to negative KT, or Y is equals to CE raised to negative 2x. Okay, so here is figure 1.7. So yung sa letter A, ito yung direction field pattern natin for the radioactive decay equation. Yung letter B is direction field siya for dy over dx is equal to negative y over x. So figure 1.8 is a solution for the decay equation. From the direction field in figure 1.7b, we can anticipate that all solutions to dy over dx is equal to negative y over x also approach the x-axis as x approaches infinity. But more interesting is the observation that no solution can make it across the y-axis. Exception, on close examination, it appears that the function y of x equal to 0 just make it through this barrier. Let's interpret the existence and uniqueness theorem of section 1.2.1 for these direction fields. For figure 1.7a, where dy over dx is equal to f of x and y is equal to negative 2y, we select a starting point x of 0 and an initial value y of x of 0 is equal to y of 0 as in figure 1.8a. Because the right-hand side dy over dx equal to negative 2y is continuously differentiable for all x and y, we can enclose any initial point x of 0, y of 0 in a rectangle of continuity. We conclude that the equation has one and only one solution curve passing through x of 0, y of 0 as depicted in the figure. For equation dy over dx is equal to negative y over x, the right-hand side f of x and y is equal to negative y over x does not meet the continuity conditions when x is 0. However, for any non-zero starting value x of 0 and any initial value y of x of 0 equal to y of 0, we can enclose x of 0, y of 0 in a rectangle of continuity that excludes the y-axis, as in figure 1.8b. Thus, we can be assured of one and only one solution curve passing through such a point. The direction field for the equation dy over dx is equal to 3y raised to 2/3 is intriguing because example 9 of section 1.2.1 showed that the hypothesis of theorem 1 do not hold any rectangle enclosing the initial point x of 0 equal to 2 and y of 0 equal to 0. Figure 1.9a displays this direction field and figure 1.9b demonstrates how both solution curves can successfully negotiate this flow pattern. Clearly, a sketch in the direction field of the first-order differential equation can be helpful in visualizing the solutions. However, such a sketch is not sufficient to enable us to trace unambiguously the solution curve passing through a given initial point x of 0, y of 0. If we try to trace one of the solution curves in figure 1.6b, for example, we could easily slip over to an adjacent curve. For non-unique situations like that in figure 1.9b, as one negotiates the flow along the curve y is equal to quantity x minus 2 cubed and reaches the inflection point, one cannot decide whether to turn or to go off on the tangent y is equal to 0. Example 1. The logistic equation for the population P at time t of a certain species is given by dP over dt is equal to P multiplied by quantity 2 minus P. From the direction field, answer the following. A. If the initial population is 3,000, what can you say about the limiting population limit as t approaches positive infinity of P sub t? Letter B. Can a population of 1,000 ever decline to 500? Letter C. Can a population of 1,000 ever increase to 3,000? Figure 1.10. Direction field for logistic equation. The solution for letter A. The direction field indicates that all solution curves will approach the horizontal line p equal to 2 as t approaches infinity. That is, this line is an asymptote for all positive solutions. Thus, the limit of p sub t as t approaches infinity is equal to 2. For letter B, the direction field further shows that populations greater than 2,000 will steadily decrease. So ito yun. Ito yung populations greater than 2,000 kasi yung 2,000 mark, ito yun. Where yung P is equal to 2 and in thousands. So lahat ng graph above 2, lahat ito is greater than 2,000 and yung trend niya is steadily decreasing. Whereas, those less than 2,000 will increase. So ito yun, yung nasa babang graph. In particular, a population of 1,000 can never decline to 500. For letter C, as mentioned in part B, a population of 1,000 will increase with time. But the direction field indicates that it can never reach 2,000 or any larger value. The solution curve cannot cross the line p equal to 2. Indeed, the constant function p sub t equal to 2 is a solution to equation 2, and the uniqueness part of theorem 1 precludes intersections of solution curves. Notice that the direction field in figure 1.10 has a nice feature that the slopes do not depend on t. That is, the slopes are the same along each horizontal line. The same is true for figures 1.8a and 1.9. This is the key property of the so-called autonomous equations y prime is equal to a function of y, where the right-hand side is a function of the dependent variable only. Hence, sketching the direction field for differential equation is often tedious. Fortunately, several software programs have been developed to obviate this task. When hand sketching is necessary, however, the method of isoc-lines can be helpful in reducing the work. Okay, so we now go to isoc-lines. An isoc-line for a differential equation y prime is equal to a function of y is a set of points in the xy plane where all the solutions have the same slope. Thus, it is a level curve for the function. For example, if y prime is equal to the function of x and y equal to x plus y, the isoc-lines are simply the curves, straight lines, x plus y equal to c or y is equals to negative x plus c. Here, c is an arbitrary constant, but c can be interpreted as the numerical value of the slope dy over dx for every solution curve as it crosses the isoc-line. Figure 1.11a depicts the isoc-lines for equation 3. So here is figure 1.11. For letter A, those are the isoc-lines for y prime is equal to x plus y. For letter B, those are the direction fields, and for letter C, the solutions to the differential equation. To implement the method of isoc-lines for sketching direction fields, we draw hash marks with slope c along the isoc-line f of x and y equal to c for a few selected values of c. If we then erase the underlying isoc-line curves, the hash marks constitute a part of the direction field for the differential equation. Figure 1.11b depicts this process for the isoc-lines shown in figure 1.11a, and figure 1.11c displays some solution curves. Okay, so we have a remark. The isoc-lines themselves are not always straight lines. For equation 1 at the beginning of this section, they are parabolas. X squared minus y equal to c. When the isoc-line curves are complicated, this method is not practical. Okay guys, so that ends our lecture 2. Thank you for watching.
Magbabaksakan dito in 5, 4, 3, 2.
channel.